Hello, everyone, and welcome to this afternoon's summer taster session, an insight into weather forecasting at Fugro. I'm Greg Dewhurst. I'm one of the events committee members for the Royal Met Soc. I'm also media advisor and senior meteorologist at the Met Office. Just a few slides to go through. Just give it another 30 seconds or so as people filter in before we sort of start, and then I'll hand over to Fred and Mark in a minute. So, yeah, as I said, welcome to this afternoon's session. It's about an hour with some time at the end for questions. There is a Q&A box on your screen, so do ask questions in there, and then we can go through them towards the end. There is an upvote button, so if there's questions you particularly like or have the same sort of ideas, instead of repeating the question, just sort of give it the thumbs up, and it should prioritize those questions more. But hopefully we can get through them all in time. To make the PowerPoint slides bigger, you can close the chat and enlarge the screen. If you're having any technical issues, it might be your browser, so you might want to sort of change to a different browser that way, but hopefully there won't be any issues. Just a few little announcements before we start. If you'd like to sign up to our Met Matters newsletter, then the information is on screen. It's a monthly newsletter full of lots of weather and climate information. And this is being recorded, so you'll be able to get the details afterwards as well. And if you are not an RMET member, then please do sign up. The more of us, the better it is, as we can do more and more events and afternoon events like this, sessions like this as well. So I'm going to hand over in a second to our speakers for the day, which are Mark and Fred. So a little background on Mark and Fred, which is on the events page as well. Starting with Mark. Mark studied meteorology and climate with a year in Oklahoma at the University of Reading. He got work experience at WeatherQuest and was a student forecaster at Meteor Group, which is now DTN as well. In autumn 2018, Mark joined Fugro as an assistant forecaster and has been a marine forecaster since 2021. Outside of work, Mark enjoys running and walks and some tennis as well. Fred Best has, just like most of us in the weather field, has an interest in the weather since a young age, qualified with a degree in meteorology and oceanography at the University of East Anglia, and has been an operational meteorologist at WeatherQuest in Norwich as well before joining Fugro. He also has the RMET accreditation and enjoys cycling and working on his allotment as well. So I will stop sharing my screen and hand you all over to Fred and Mark.
Yep, hi everyone. I'll just quickly get my screen shared.
Lovely. Okay then. Good afternoon, everyone. Welcome to an insight into weather forecasting at Fugro. I am a marine forecaster here. I'm Mark Skinner.
Hi, I'm Fred. Thank you for joining in. Before we get going, just possibly a bit of a repeat of what Greg's just gone through, but just a bit of background about the two of us. So I'm Fred. Like Greg said, I studied meteorology and oceanography at UEA from 2014 to 2018. I then worked as a operational meteorologist at WeatherQuest. I joined Fugro here in 2022 as an assistant forecaster, and then became one of the marine and duty forecasters in 2023 until now.
So as Greg was saying, I did the Masters of Meteorology and Climate with a year in Oklahoma at the University of Reading from autumn 2014 to the summer of 2018. I got some work experience at WeatherQuest towards the end of my degree outside of term time, 2017, 2018. I did some newspaper work as a student forecaster for Meteor Group in the summer of 2018. And I became an assistant forecaster at Fugro in October 2018. And then in the summer of 2021, I was promoted to the marine or duty forecaster position, and I have held that position since. So talk outline for today. So who are we and what do we do? So why do we provide weather forecasts to different clients and who are these clients? A typical day in the life of a forecaster in our office, an overview of some of the regions we provide forecasts for and the various challenges that we come across, and how we integrate our own in-house model data and observations into our forecasts. And then at the end, we will have a question section.
Great, yeah. So just a little bit of background about Fugro and what we do other than weather forecasting. So we're based here in Wallingford in South Oxfordshire, but we're headquartered in the Netherlands. We've got offices in 57 countries with over 11,000 employees. So yeah, we do work right the way across the globe in all sorts of different industries. So what do we actually do? Many of you may not have heard of Fugro, but basically what we do is we use geodata to unlock insights. So what actually does that mean, and what is geodata? Basically, geodata is data that's collected from the natural world. So what we do is we kind of collect and use this information, turn it into practical advice to help clients do safe, sustainable, and efficient operations in sectors such as like energy, water, and infrastructure, before, during, and after a project, so right the way across a project life cycle. So for example, if a client was wanting to kind of build a new wind farm, say, in the North Sea, Fugro could provide geophysical and geotechnical surveys. So that's basically assessing whether a site is suitable for such construction. So a geotechnical survey is basically where you drill a borehole into the seabed. You collect soil samples. We have a team here in the Wallingford office that analyse the soil samples, and basically from this you can ascertain whether the ground is actually suitable to build a structure like a wind farm. Geophysical survey is similar, but it's kind of less invasive. It uses kind of electromagnetic measuring that to sort of get similar information. But it's all about assessing whether a terrain is suitable for a site. In the example of if you wanting to build an offshore wind farm, you would also need hydrographic or bathymetric surveys. So this is kind of like mapping the seabed basically to see what the terrain is like, whether it's suitable for building something like a wind turbine, and where you'd be able to lay cables back to shore to get the power in. So that's really important to know what the surface of the ocean looks like. We have these Met Ocean LiDAR buoys, which basically measure the wind speed at different heights. They measure the wave heights, they measure the currents. So that's kind of all about seeing whether a site is feasible for, say, like a wind farm, to see what the winds are like. It's also important for during construction and during the operational phase to kind of have real-time data, which also helps with weather forecasting. So weather forecasting is a relatively small department in Fugro relative to the rest of the organization. But obviously, as we're going to explain why shortly, it's very important to know what the weather's going to be like for all sorts of reasons. So hopefully that's just a kind of a bit of an idea of the kind of things Fugro do. It's not limited to this, but these are kind of some, I guess, key examples of the kind of things that we work on.
So why do we provide weather forecasts? So long and the short of it is it's to ensure that our clients can work safely and effectively. So say you're working on a rig or a wind farm out in the North Sea, you'll want to know when it's safe to go out to do the work. And then when you're out there, it's important to know if the weather is going to change, whether you need to take shelter or stop the work you're doing. It's all about minimizing risk, making the uncertain more certain for our clients. Some people do just use this for simple insurance purposes. Basically, if something happens, they can't get the insurance through if something goes wrong and without being covered. So yeah, long and the short of it is it's just about making sure that our clients are safe and they can work to their time frame and they can work effectively.
So this is just a kind of overview of some of the sectors that we work with, provide forecasts for. So a lot of what we do is for the offshore marine sort of sector. So kind of primarily that's working with companies in renewable energy or oil and gas energy, doing all sorts of different things from kind of similar surveying and mapping to just maintenance, installations, things like that. All of these things require weather forecasts. We do provide forecasts for vessels that are going surveying. So a lot of this is with the Fugro vessels, which go out and do the like hydrographic or geotechnical surveys that I mentioned before, but also other customers that are wanting to do surveying. We provide forecasts for kind of just general shipping. So if you're wanting to go from A to B, kind of across the Atlantic or something like that, you'd want a weather forecast to make sure conditions are good, so you know what you're expecting. And then basically just any kind of other offshore operation that you can think of is likely to require a forecast. So for example, going out and servicing weather buoys, laying seabed cables, things like that. So a whole range of different offshore operations. We do some forecasting for the on land as well. So primarily in the construction industry. So this is for kind of crane and knowing the wind speed and the risk of lightning at crane height is really important, primarily for safety reasons, really. And then finally, media, we do some forecasting for like the filming industry. So that's quite a different type of forecasting, really. It's more about, instead of wave height, wind speed, it's kind of like whether it's going to be cloudy, whether it's going to be sunny, so that they've got know what conditions there's going to be for them to be able to film the scenes that they want to, basically. So that's a bit of a different kind of forecasting to the rest of it. But yeah, it's a whole range of things. Primarily, a large proportion of what we do is for Fugro's own fleet of vessels. So that's about 45 vessels around the world, working on all sorts of different projects. So just got a few examples of some projects that Fugro have worked on recently, just to kind of flesh that out a bit, give you some insight into some of the projects that we've worked on. So this is a recent one from a couple of years ago. The government of Curacao in the Caribbean, little island here, basically asked Fugro to assess the potential for offshore floating wind farms in the waters surrounding the island. So this is the Fugro Basilis that went out and surveyed the subsurface and marine environment, doing some of those surveys that I talked about in the earlier slide, basically just to see what the conditions were like, whether it was suitable for offshore wind. The Caribbean is quite often dominated by fairly predictable trade winds that persist throughout a lot of the year. So they have fairly persistent winds. So it's quite a good area for looking at wind. So yeah, that's what that vessel was doing. Something that's ongoing at the minute. This is a sort of bit of a different project, really. It's quite an interesting and exciting project that's ongoing. So basically, there's several Fugro vessels mapping around the coast of Italy, mapping the coastal and marine habitats that around the coast. So particularly looking at seagrass. So seagrass is really important because it, as well as being a kind of quite vibrant habitat, it captures carbon from the atmosphere around 35 times faster than tropical rainforest does. So it's really important as a carbon sink. And so basically understanding how widespread the habitats are and where that they might need to be restored is really important. So the government in Italy have got this marine ecosystems restoration project where they're wanting to map all these habitats, understand what's going on, understand where needs to be improved. So yeah, Fugro have been doing that mapping from using the vessels, but also mapping using airborne LiDAR, which is basically kind of sensors from an aeroplane, and also using satellite imagery. So that's a really exciting project that's still ongoing and will be going on till 2026. Something you might be a bit more familiar with. We provided weather forecasts during the construction of the Shard in London. So as I mentioned earlier, wind speeds at different heights and the risk of lightning is especially important when you're working at height. But Fugro also provided ground investigations and surveying during the construction of the Shard. So yeah, we were involved with that as well. And then one final example. So this is something that's a bit different. This is one of our newer autonomous vessels, the Fugro Vaquita. You may have seen this. I think it was in a piece in the BBC either last year or the year before. But basically, these are quite new vessels. They're fairly cutting edge, and they're controlled by, there's a team in Aberdeen, in the Aberdeen office, the remote operations centre team, and they control these remotely. So there's no crew that goes offshore with these. And in this case, the Fugro Vaquita was carrying out pipeline surveys in the Dutch part of the North Sea. So basically detecting anomalies in any pipelines, checking for maintenance as they can get damaged by other things going on the seabed. So this is really important to make sure that there's no damage to the pipelines. And although that there's no crew on the vessel, so when we're thinking about forecasting, you're not necessarily thinking of like a risk to the safety of the crew, but it's still really important because it impacts the quality of the data. So if the vessel is moving all over the place in high seas and it's trying to survey the seabed, the data won't be as good quality, whereas if the sea is quite calm, it will be able to get good quality data. So it's really important for the crew to know what the forecast is, so that they can choose good times to go out and do their surveying to get good quality data. So yeah, I hope that's just a bit of an overview of some of the projects that we've worked on and provided a forecast for, basically.
So Fugro, so we're a global company. So we have 3 forecasting offices worldwide. We have our office here based in Wallingford, covering the Americas, eastward, so across Europe and Africa. We've got the Dubai office, which covers the Middle East, India, and some of the Indian Ocean. And we've got the Singapore office, which is covering the Asia Pacific and Australasia. All of our offices operate 24 hours a day, 7 days a week, 365 days a year. So a typical forecaster's day here in Wallingford. So our shifts tend to be 12 hours, 7 a.m. to 7 p.m., or vice versa for night shifts. And we're contracted to do forecasts all around the locations that I was specifying on the previous slide. So if you're on the marine bench, for example, so you'll be covering places all around the UK, so the North Sea, the Irish Sea, Celtic Sea, up through to the Norwegian and Barents Seas. The assistant forecasters will focus on the Mediterranean across West and South Africa. The marine forecasters also look at, say, the northeastern seaboard, so towards Nova Scotia, Newfoundland, New England, and then the assistants would be doing things like the Gulf of Mexico, the Caribbean, and South America, and the parts of the South Atlantic. We do get ad hoc requests, as Fred was alluding to earlier, from, say, media and crane clients. We recently did the forecast for the latest Paddington movie, for example. Throughout the day, we'll get lots of client emails and calls. Could be for a new project somewhere offshore, could just be as simple as a change of forecast location, or a change of warning limits if the work they're doing is changing over time. We also provide more particular forecasts as well, such as squall warnings, and during the hurricane season, tropical storm warnings. So before moving on to some examples of some of the areas we forecast for and the challenges we sometimes face, we're primarily marine forecasters. So in case some people aren't that familiar with marine forecasting, we're going to be using several phrases and words over the next several slides that some people may not be particularly familiar with. So I've just decided to create a definitions page here for some of the phrases and words we'll be using. So starting from the top, so fetch. So this is just simply a distance over the ocean surface where the winds are blowing from a consistent speed from a particular direction. It's not impeded by land, so therefore the winds can transfer all their energy to the ocean surface, which then generates waves. Once these waves have left the fetch area, they've left the generation area, they then propagate away, and this is known as swell. And so this generation area may be like an area of low pressure, a hurricane, that sort of thing. Wavelength, that is simply the distance from one wave peak to the next. Wave period, and this is the time taken for 2 successive wave crests to pass a location. Significant wave height and maximum wave height, which are often very important to our clients. So the significant wave height is the average of the highest 1/3 of the waves, and the maximum wave height, Hmax, and they're often abbreviated as Hsig and Hmax, and is the average of the highest 1/10 of the waves. Here's just a nice graphical illustration. I'm sure if any of you can think back to your GCSE physics days. So you can see it graphically illustrated the wavelength here from peak to peak, and the period here from peak to peak over a period of time.
Cool. Okay. So for the next sort of section, basically, we just want to highlight a few areas that we provide forecasts for, and some of the things we have to think about in these different areas, and how we have to kind of intervene on the forecast over the models, and some of the things we have to consider, and the challenges that there are. Before we get going, I'm just going to quickly try and change this mouse to a laser pointer. That's a bit better. Okay, so first off, we provide quite a few forecasts in the Gulf of Mexico. Just a bit of a summary of the weather that we tend to see in this part of the world. So from late autumn through till early spring, the weather tends to be dominated by cold fronts, which move southeast across southern USA across the Gulf of Mexico, and then continue moving further south and tend to weaken. These can be very active, so we can have a lot of lightning as the fronts pass, the risk of squalls, which is kind of instantaneously very strong winds, which Mark will talk a bit more about in a little while. And they also generate large amounts of swell. So you get strong northwesterly winds behind the front, which generates lots of waves, which then move southeast across the Gulf of Mexico. So when these fronts pass, a lot of models struggle to kind of capture the peak of the winds and the I guess the peak of the wave heights as well. So we have a modeling team here in the office which produce high resolution models. They capture this better than the global models, but we still need sometimes to, as forecasters, go in and intervene on the forecast to lift the wind and waves above the models as the fronts pass. There's various observations dotted around the Gulf of Mexico, which can kind of help us see how the forecast is doing as the fronts move across, and we can kind of try and push that forward to work out what the likely situation is going to be when it passes any sites. But quite often it needs a reasonable amount of intervention, despite the higher resolution models capturing it a little bit better. And I've got in the next slide an example of one of these events. The rest of the year, so from late spring through till early autumn, generally the pressure pattern's quite a bit slacker, especially in the southern Gulf of Mexico. So by slacker, I mean there's lighter winds, not a lot going on synoptically, so in terms of big weather systems. But you do get slow-moving storms which develop inland across particularly southern Mexico, the Yucatan Peninsula, and they drift offshore. So that's something you kind of have to watch out for. The main threat to vessels in the Gulf of Mexico this time of year is tropical storms and hurricanes. So we'll also produce warnings for vessels and clients that are in range of a storm. So this here on the right is an example from Hurricane Rafael. It's when the Fugro Explorer was doing some work in the northern Gulf of Mexico. And basically this is just to make sure that they're aware of where they are in relation to the storm. They know where the storm's moving, what the strength of the winds are going to be like. And it's just to make sure that they are aware of where they need to go to get away from that, to be safe. So they're not, in this case, moving southeastwards into the track of the storm. They're fully aware of what's going on and can move away. So yeah, that's all about just making sure that the vessels and the crew on the vessels are staying safe. So one example of these events, a cold front moving southeast from this year. So this is an example from the 7th of April this year. This satellite image on the left is from 6:20 UTC, so that's about 1 a.m. just after midnight local time. You can see here the cold front in here on the satellite image, one in that blue line there as well. 5 hours later, see the cold front in here, but a line of thunderstorms had rapidly developed ahead of the front and were moved northeast, kind of along the front. So this is a kind of situation where there are numerous hazards to warn for. It's quite a tricky, kind of rapidly evolving situation. So it's one where often the models will struggle to kind of capture exactly what's going on here. So you have to be monitoring radar, satellite imagery, lightning imagery as you're writing forecasts, and in the lead up to forecasts, sort of sending forecasts and afterwards, to make sure that conditions are panning out as you expect, because sometimes they can evolve in a different way, and in those situations we would need to update the forecast. You can see in this case there's a lot of lightning, so this is basically 24 hours of strikes, the red strikes being the oldest until the white strikes being the newest, as the front moved west to east. So you can see a lot of lightning. Any vessels or sites in this sort of area would likely have seen some strong winds, so that's something we would have to kind of look out for, make sure it was in the forecast. So this is an example of a bit of a active situation with a lot going on. Just a few more charts just to kind of explain a bit more what we're talking about. So this here is winds. If you're unfamiliar, this here is showing northwesterly winds, and the color scheme is the strength of the winds. So this here's the front in here. Behind that's where we've got these strong northwesterly winds. In the southern Gulf of Mexico, you can see here kind of getting up to strong to near gale force winds. Associated with that, this is the wave heights, the significant wave heights. and the maximum wave height. So like Mark mentioned earlier, the significant wave height is kind of the average height you're going to generally see. The max wave height is what basically the maximum waves that are sort of forecast. Then you can see in this situation, southern Gulf of Mexico into the Bay of Campeche, we're looking at waves of up to 6 to 8 meters. So these events can bring pretty stormy seas, and it's the kind of situation where any vessels would want to be moving away from this kind of area. So it's important to try and capture the magnitude of this accurately when we're forecasting. And like I say, we have to often intervene to lift the wind and waves above the models as these fronts pass, as they often struggle with it. And one other thing to note as well, this here is a kind of a radar simulation, I guess. It's the precipitation rate. And you can see this model here is kind of picked up the front and separately the band of showers. So it's got a good idea of what might be going on, but obviously exactly where it's going to develop the showers is going to be a struggle for the model. So it's good to get an idea, but we need to really focus on using observations and radar satellite imagery in situations like this, as the models struggle to pick up a lot of the specific detail.
Okay, so another area that we forecast for is in West Africa. So I've sort of split this into both the marine environment, so I've done a section on that, and then there's a later section about the atmospheric environment and the conditions that are experienced by our clients in this part of the world. So off West Africa here, so we do a lot of forecasts around the Gulf of Guinea, in this area, in this part of offshore West Africa. The primary concern from a marine environment for our clients in this area is swell. And this swell is generated by deep areas of low pressure here in the South Atlantic towards Antarctica and the Falklands. And so this swell then propagates out up towards West Africa and the Gulf of Guinea. So I think in terms of waves and in terms of swell and what concerns our client, it can depend upon the size of the vessel that they're on. So I've got some nice little illustrations here as to how different waves at different periods and different wavelengths can be more or less dangerous to different sized vessels. So if we look at this first example here, so we've got a 2 meter significant wave height, we've got a short period of 6 seconds with a small vessel. So with the wave being at a short period, that means the wavelength will be shorter, so similar to the vessel length. So therefore the vessel will feel large impacts from those waves, and the greater the significant wave height will be, the greater the impact on the vessel will be. However, if we now go to another scenario where you have long period swell, so 12 seconds, so therefore the wavelength will be longer, so therefore the vessel in this case is significantly smaller than the wavelength, and therefore it will experience a much smoother ride. Vice versa though, so if we now have a really large vessel experiencing short period waves, so in this case again 6 seconds, the wavelength is much smaller than the vessel length, so therefore the impact on the vessel motion is limited. But if you are a large vessel experiencing long period swell with a long wavelength, again, just like with a short vessel, but for the shorter period, the wavelength is therefore similar to the vessel length, so therefore the vessel will feel a larger impact from those waves. So on this slide here, I've got some nice images here to illustrate how swell trains propagate away from their swell generation area, from the fetch area. So you've got a deep area of low pressure here off of the Falklands, and the waves that are generated by those extremely strong winds then propagate out. As they propagate away, the waves with the highest periods propagate out faster than the waves with the shorter periods because they have more energy. And so that's nicely illustrated here by the darker yellows and oranges and reds. So the darker the colours are here, the longer the period is, and then the shorter period waves then follow later in the swell train. And so you can see them there propagating northeast up across the South Atlantic towards the Gulf of Guinea and West Africa. So now let's have a look at the atmospheric environment. So off of West Africa, it is all dominated by the intertropical convergence zone, which is the primary driver of the weather in this region. So when the ITZ is nearby or overhead, you can get lots of thunderstorms being generated. These storms can generate frequent lightning and squalls, which I'll go into more detail about shortly. And of course, this can pose significant danger to vessel operations. With nearshore forecast in this part of the world, in many respects, it's a bit like persistence forecasting because you can get a very typical wind cycle dominated by sea and land breezes. and sometimes these can converge and generate thunderstorms as well. During the winter months, however, the ITCZ sinks south, and this allows dust outbreaks from the Sahara to impact West Africa, and this can result in significantly reduced visibility and poor air quality, again, potentially having an impact on operations, and this is known as Harmattan season. So this is an example of a squall generated by this lovely mesoscale convective system here, moving off of West Africa. So there is, if we have a look at the plot here, you can see a very clear, massive, huge increase, violent increase in winds as the squall passes the location. So if we're just talking about sort of like the life cycle as the squall goes past a location, so as the MCS approaches, you basically have what's known as, so there is some truth to there being sort of like a calm before the storm. So there's what's known as a pre-squall low just ahead of the system. And when you're in the middle of that, the pressure gradient can slacken, and so you can get quite significantly lighter winds. Squall passes overhead, and of course the winds increase dramatically. And the official definition of a squall is a sudden increase in winds of at least 16 knots or 8 meters per second, attaining a mean wind speed of at least 22 knots, so 11 meters per second, and lasting at least a minute. So you can see that, yeah, there's a violent increase in winds, and then of course it drops off quite dramatically straight afterwards. The winds then do sort of bounce about here at this part of the graph. So as the system moves away, you get these MCSs or mesoscale convective systems. You can get what's known as a wake low astern of the system, and that can generate some stronger winds as well as it interacts with the higher pressure around it. Now going from extreme rain to extreme dry and dust. So this is looking at these satellite images here. So this is an example of Harmattan season. So the dust here I'm pointing out is generated from the Bodley Depression in Chad. So during the winter months, high pressure becomes centered over North Africa, and it can stay pretty stationary sometimes for weeks on end. And what it does is it generates a northeasterly flow, northeasterly winds that basically act as a low-level jet, and these winds get funneled between the Tibesti and the Anidi Mountains in this region here, and they then blow across the Bodley Depression. And every morning the sun comes up, there's lots of heat transferred to the surface, and so you get turbulent mixing going on, and that forces the jet to the surface, and then that kicks off the dust from the Bodley Depression, and that then spreads southwest into Nigeria. And times it can spread much further. It can go all the way over to, so say the Cote d'Ivoire, it can move into the Gulf of Guinea, Cameroon. The visibility is often reduced to say 1 to 5 kilometers, but sometimes in the really strongest outbreaks, it can get less than 1,000 meters as well. So this is an example of typical visibilities during a Harmattan event. So this is at Lagos, but for some near offshore forecasts, it can be quite similar as well. So the visibility tends to vary a bit during the day. So during the afternoons, during Harmattan is when the visibility is at its greatest, at its furthest distance, because of turbulent mixing, which reduces the dust concentration from daytime heating. Overnight, though, of course, the air cools, the surface becomes cut off from higher up in the atmosphere, so the boundary layer gets cut off. So you end up with the dust concentration increasing, and this results in poorer visibility. Occasionally, the dust can also act as condensation nuclei, and so you can also get fog at times during Harmattan season as well.
So somewhere a bit closer to home, forecasting in the Mediterranean Sea. This can present numerous challenges, but mainly because of how complicated the coastline is. There's lots of different islands. There are in the Mediterranean lots of different areas where small-scale, low-pressure systems form, which generate areas of swell which move around. And yes, it can be quite a lot going on, illustrated by all the different seas that we've got in here. You also get small-scale features such as Mistral winds, which are strong north-northwesterly winds coming off France, Bora winds, which affect the Adriatic Sea, and one that I'm just going to focus on, which can present a particular challenge to forecasting, is the Etesian winds. So these affect the Aegean Sea, and basically it's formed by high pressure over the Balkans and Greece interacting with low pressure across Turkey. And air around high pressure goes clockwise, around low pressure it goes anti-clockwise. So when these two combine, you can get strong north-northwest and north-northeasterly winds. Generally the area is quite dry, cool, and brings clear skies, but it can bring very strong winds. which can be amplified by a lot of the different islands. So when we're forecasting in this part of the Aegean Sea, it can be quite tricky, and you have to rely on a lot of observations that are in the region. The Etesian winds are actually linked to the Asian monsoon as well. So when you get low pressure over the Indian subcontinent during the monsoon season, it deepens this trough across Turkey, which can amplify this as well. So this is something which we kind of have to, when we see that this is kind of in the forecast and likely to form, we have to sort of think about what we can do with the forecast to kind of intervene on it a bit. So this is one example from April this year. So this is a pressure chart from the Met Office, showing high pressure across kind of northern central Europe, extending a ridge down into Greece. We've also got low pressure here over Turkey with some troughs as well, and these interact to produce these quite strong north to northeasterly winds. So you can see this is just one time shot from 12 o'clock on the 29th, but basically you can see we're getting to kind of near gale to perhaps close to gale force winds. And although this is what the model is showing locally, it would be likely that around some of these islands, the winds could be kind of locally stronger than what's being suggested here. So yeah, it can be quite tricky to kind of nail on exactly how strong the winds are going to be sometimes. So this is from the same event, just showing the onset of these winds at a site here, Syros Airport in the kind of northern central Aegean Sea. Before the onset, winds generally quite light. The red here is the wind speed, the grey is the wind direction. So we've got fairly light winds, less than 10 knots, generally west to south or south-southwest. And then late on the 27th and into the 28th, the winds turn around to the north, up and down like this because it's sort of flicking between north-northwest and north-northeast, but generally from a northerly direction, wind speed increasing, and we're getting up close to near gale force winds at times. And once it sets in, sometimes it can be kind of a diurnal thing, but in this situation, it's persisted for 3 or 4 days before slowly easing off. So yeah, the winds are tricky in terms of getting the magnitude right, but what's the hardest part sometimes can be the impact that it has on the wave heights, and particularly when you've got strong northerly winds over the northern part of the Aegean Sea, is how much of that swell and waves that are generated move through this chain of islands into the southern part of the Aegean Sea. And the reason that this can be quite tricky is that different wave models resolve these islands quite differently. So this is just two wave models out of kind of many that we look at, but just to highlight the differences really in how the islands are being resolved by the model. So where's white is basically what the model is resolving as land. You can see in this case, there's a lot of islands here that aren't really being resolved too well or at all. So a lot of waves, a lot of swell is going to get through this region in this model because there's not many islands being resolved correctly. In this model on the right, although it's still not resolving all the islands, you can see there are more here that are kind of highlighted white. So there's slightly better resolution in terms of modeling of the islands. So you can kind of see the impact in these two images that this has. So the one on the left, although initially it does have more swell as the wind, the atmospheric model that's driving this wave model likely has stronger winds initially to start with. Nonetheless, it still allows a lot more of this swell to move through the Aegean Sea compared to the model on the right. So you can sort of pick out a few areas, for example, around these islands, where south of the islands, it's modeled much better that the wave heights are much lower than to the north, and similarly around this whole island chain here, it's more realistic. Whereas in this model, there's in some places little or no reduction in wave heights as there's no islands modeled to block it. So basically, when we're kind of looking at writing forecasts in these areas, when it comes to the waves, we've got to really look at which models are resolving the islands best, where our forecast is in relation to all the different islands, and how we might need to manually intervene on the models to either bring down the wave heights or in some cases increase them to make it more realistic. So it can be quite tricky and sometimes requires a lot of intervention by the forecaster. So just one example of how you might kind of go about thinking about this is, say we've got point F here, if we were writing a forecast for. a lot of these islands, as you saw in the previous slide, weren't really modeled that well at all or resolved that well by the model, either of those models. So we kind of think about where, in a northerly flow, where is the swell likely to come from? So I've kind of just roughly drawn on here, basically the sort of main directions that we might see the waves move around these islands. So yeah, that's basically what we'd need to consider. We get our forecast location, look at where the islands are, amend the forecast accordingly, depending on which models are, doing what and how much swell that they're bringing through. So can be, especially in the Artesian winds situation where all the swell is coming from the north, there can be a lot of forecaster input that's needed. For the rest of the year, for this part of the world, a lot of the swell actually comes through this gap here between Crete and the rest of Greece. And that can be a little bit easier because it's really the only entry point for swell generated in the rest of the Mediterranean Sea. It's only really trickier when we've got these northerly winds moving swell southwards. Obviously, if you've got a forecast up here, then from the south is also going to be tricky. So it can be variable, but the Artesian winds present a particularly tricky situation sometimes for forecasting. So I kind of alluded to it just now about waves moving around islands, but just kind of a bit more detail on what exactly goes on there. There are two main processes of waves sort of moving around islands and obstacles, and that's refraction and diffraction. So they kind of give a similar outcome to when we're thinking about the forecast, but they're different processes really. So wave refraction. So you might know of wave refraction from think about science where the waves change direction, like light waves will change direction as they move through a medium of a different density. It's a similar kind of thing in the ocean. So basically waves refract in the ocean due to a change in sea depth. So if you have waves here moving out of deeper water into shallower water, as the waves move into the shallower water, they slow down, the wavelength decreases, and the waves turn basically towards the shallower area. So they kind of move around the island depending on the local depth sort of situation. So that's one way that waves move around obstacles. The other main way is wave diffraction. So this occurs when waves change direction to go either through a gap or around an obstruction. And basically they do it in this manner. So they come through the gap and then spread out and kind of bend in a way around the islands. And the amount of bending, so to speak, is dependent on the wavelength. So the longer the wavelength of the waves in relation to the size of the gap, then the more the waves will move around the island. So yeah, that's kind of I guess an overview of some of the things we think about in the Mediterranean.
So next area that we often do lots of forecasting for is the Baltic Sea. So the marine environment, it tends to be dominated by more local wind wave than swell generation. So what do I mean by that? So the Baltic Sea, in many respects, it's like a big inland lake compared to the South Atlantic. The waves can struggle to actually get away from their generation area. And so when they're in their generation area, they're referred to as wind waves. So if you imagine you're on a beach and you've got a strong onshore breeze coming in and the waves are all looking very jaggedy, whipping up on the ocean surface, so that's your wind wave. And because of the small basin size as well, the waves do not have time to get particularly, especially large and develop at an especially large wavelength and therefore a long period. So it tends to be dominated by short period swell. There's also lots of islands, just like in the Mediterranean, so that can lead to lots of wave refraction and diffraction. Atmospheric environment, compared to West Africa, you've got the jet stream dominating weather patterns, so generating a lot of synoptic scale, deep areas of low pressure. These can generate in the winter months, lots of snowfall and lots of ship icing, through winter into spring. When you get areas of high pressure over the area as well, you can get plenty of fog, especially during the spring months when the sea surface temperatures are still relatively cool. And during short periods in the summer, you can get convective precipitation, sometimes on very, very rare occasions, maybe even something up to potentially a squall. But again, that's very, just for short periods during the height of the summer. So on the next few slides, I've just got several examples of the sort of weather we can experience across the Baltic Sea. So this example is from 12 UTC on the 2nd of February 2024. So you've got generally west-southwest to southwesterly winds. So if we look at this plot here, And the winds are peaking 22 to 28 knots over the southwest Baltic Sea. Because I say it's fetch limited, it's an enclosed basin. The wave heights in this case are getting particularly strong, particularly high, sorry, between 1.5 and 2 meters. The model as well, like Fred was alluding to earlier, in this case has neglected the island of Bornholm, looking at the red circle here. So it's always important to see how the models are doing compared to the islands. And the limited fetch, as I alluded to on the other slide, you can't get such high periods, such high wave periods with limited fetch size. So therefore, unlike in the South Atlantic, where we had lots of yellows and reds with high periods of, say, 17, 18, 19 seconds, in the Baltic Sea, it's been limited to, say, between 4 to 6 seconds. So here's an example. So we've had lots of work over the Western Baltic Sea over the years, and here's a couple of areas where we have to consider the interaction of the winds and the waves with the various islands. So if you look at point C here, so all the southwesterly waves, of course, will be blocked. However, if we look at point A, so if you've got like a strong southwesterly flow, but your forecast location here is at point B, that strong southwesterly flow will generate southwesterly wind wave that will then become swell, which will then refract around here to point B. So at point B, they'll experience west-northwest to northwesterly waves at their location. So long as they're as long as they are in sufficiently deep water as well, the wave height will be reduced because energy will have been lost as the waves refract and diffract around, but the wave period will be conserved. So here's some nice examples of the winter weather that you can get over the Baltic Sea. So if we look at this plot here, you can see temperatures across the northern Baltic here well below freezing. And the winds in this area as well are blowing at, say, between 22 to 28 knots, so strong winds. So you've got low 2-meter temperatures, you've got strong winds. The sea surface temperature, looking at this plot here, is around 5 to 6 degrees. So, of course, these winds could whip up some waves that could then generate some spray around the vessel. The vessel, of course, will be way below freezing because, of course, the air temperature is around -4 degrees. So that could pose a risk of ship icing. In this case, probably light ship icing, but again, with stronger winds, with higher waves, with more spray, you can get more significant ship icing. And that can, if it in severe circumstances, it can actually destabilize the vessel as it clings all around it and cause it to capsize. So it can be a significant risk to offshore operations. Another thing that you may find in this area as well is you've got these strong winds moving offshore. Of course, the land temperatures are very, very cold. And so you've got this very cold air going over a warmer sea surface, so it might pick up a little bit of moisture. Of course, the air will still be very cold, so that moisture will condense out and could generate some sea smoke in this region. And it will be made up of soup called droplets. So these droplets can also impact the vessel and also actually freeze on contact as well. And here's a nice example of when the weather over the Baltic Sea can be particularly nasty. So this is Storm Abel on the 2nd of January 2019. So as you can see here, this plot here was taken so it moved from west to east. So it became centered over the Baltic states at this point, and this is taken at 6 Zulu on the 2nd of January. So it generated severe gales over the eastern Baltic Sea, significant, so very strong winds, and these winds transferred their energy to the ocean surface, generating unusually large waves because, of course, over the eastern Baltic, from that direction, the fetch is actually is quite large. So yeah, the other things to consider beyond the large waves that they were generating is, and again beyond the severe gales, you've got lots of precipitation, and of course with the temperatures being low enough, you've got lots of snow, reducing visibility. With rapidly deepening areas of low pressure, you can get what's sometimes known as sting jets as well. Across this part of the world, we can experience them here in the UK as well. So that's another thing to also look out for. And you can also, just like on the previous slide, towards the Gulf of Bothnia up here, the temperatures are sufficiently low that you could also get a risk of some ship icing. So here's a nice time lapse of how the winds transferred their energy to the ocean, to the ocean surface. Those winds then generated lots of waves, which then propagated as swell down towards the coast, the north coast of Poland. You can see how the model has the waves interacting with the various islands and how in some areas it's picking it out well and in other areas it isn't. So, for example, is picking up Faster Island and Gotland quite well, although you've got this little peninsula sort of sticking out here. You may find the wave heights are a little more reduced in here, and as it then transfer, those waves propagate out towards the southwest Baltic Sea. Again, how those waves interact in the model compared to reality is really important to take consideration of.
Cool. Just to sum up, I hope that's giving you a bit of an idea of a lot of the different challenges we have to consider and think about in different parts of the world. So just kind of finally, really, what data do we use and how do we use it and where do we get it from, really? So this is kind of just a bit of a schematic, really, to show where we get some data from. So we use a lot of models from global modeling centers, so things like the ECMWF, NOAA, Meteor France, for example. We use a lot of models that are produced by those organizations. Like I mentioned earlier, we also have an in-house modeling team which develop higher resolution models for some areas of the globe, and these are really, really good at particularly around the coasts, or for sort of smaller scale features. They can be really good at picking up. So we kind of complement the global models with these in-house models. We use satellite data, radar data, lightning data from remote sensing type applications. And then, like I mentioned, we also use real-time observation data from Fugro vessels, but also a lot of the metocean buoys that we have in various places, but also any other freely available observation data. The more observation data you can kind of get hold of when writing a forecast, the better you're able to make that forecast, because you can kind of combine these and see which models are performing well at any given time, which models are handling certain weather situations better, and that's kind of our role, really. So it's kind of why that having a forecast written by someone is the advantage of over just a kind of looking at raw model data, is it picks out, we can pick out all these kind of intricacies. We can look at which models are performing better, using observation data to kind of tweak the forecast accordingly to make sure it's kind of accurately representing what's going on. So that's kind of our role, really. And then we send the forecast out to the vessel, and then it's a little bit of a circle, really. The vessel observations then come back to us. They go to the modeling team as well, and they can help improve the modeling, which then comes back to us and helps us improve the forecast. So it's kind of a bit of a circle of improvement, really. We can use all these different data sources to improve the forecast and make it as accurate as possible. And then just finally, just to show how we can basically visualize this from the Fugro vessels. So this is Fugro Explorer's kind of online panel, basically. You can see in blue here the real-time wind observations and wave heights. That's overlaid in red by our forecast, which is updated accordingly onto that. We can see when the vessel is actually at the site that they're receiving a forecast for, because obviously they're kind of going off to port to refuel or to pick up crew changes and things like that. So they're not always on site. So we've got to make sure that when we're actually looking at the observations that they're for the right place. And that's we can see here. So I guess the point of this is that we can see when the forecast is performing well. There are some periods where you can highlight where perhaps it wasn't performing quite as well. So for example, here, so actually maybe the wave height was a little bit below the forecast, likewise with the winds. So we can look at what the weather setup was and identify which models were actually performing better in that situation. And then that helps us in future situations like that going forward. And you can see that kind of over the next couple of days, we kind of did that, really. So yeah. So it's all about kind of using the observations to improve the forecast and not just sending out raw data that you might find freely available. So yeah, I hope that's kind of giving you a bit of an insight into what we do, how we do it, and why we do it. And yeah.
Any questions?
Any questions we'd love to answer? Just stop sharing my screen.
A few minutes left, so see what sort of questions are coming through. Up to what spatial resolution? This was my question as well that I was going to ask. What is the resolution of your in-house models? Oh, I can't hear you.
Sorry.
Oh, yeah.
It kind of varies model to model depending on what's necessary and depending where the model is representing. So it does vary. I must admit, off the top of my head, I don't know the exact resolutions of some of the models without double checking, but they're especially kind of around the sort of places that we have them for. They definitely can improve in some situations, especially around the coasts, because that can be especially if people are doing vessels are doing nearshore operations. The way that the waves interact with the land can be quite tricky for models to pick up on. So they can really help to improve that.
Lovely, thank you. Do you get to go on detachments, go to other offices around the world, or sort of do offshore sort of work within your role?
So before COVID, yes, going offshore was quite, for the more senior forecasters, of course, and those that had done the offshore training would go offshore to these vessels. And of course, that can be beyond, incredibly useful, because of course you're right there, you can see it out the window, what the waves are doing, what the winds are doing, etc., etc. But since COVID, a lot of it now is onshore, offshore. So you would actually work from the office or even from your own flat or home, and you'd then provide the dedicated service. You'd then provide the dedicated service from there, and the people on the vessel will then provide you with all the information regarding observations and stuff. Basically, COVID's pretty much put a stop to that, unfortunately. But before, in the pre-COVID days, yes, we did.
It kind of depends on what the particular vessel or client wants, really. Like if something can be done as well from home, it's a lot of effort to get people offshore. But if it's something that they want, it's still I think it's still doable, depending.
Another question just come in. How do you find explaining the weather risk and forecast uncertainty to someone that may not have a meteorological background? Is it challenging?
It can be. It can be challenging, yes, because sometimes, it depends upon, as you say, quite a lot of people don't have, may not have a particular good understanding of how uncertainty grows over time through weather forecasting, whether that be within the atmosphere or within the ocean. But the way we sort of like to do is we sort of, we'll describe the confidence, say, as moderate at mid-period, low towards the end. We steer clear of percentages because, again, people can interpret that in various different ways. But yeah, we try to be as concise as we can. And if a client is ever unsure of anything, we always say to them, do let us know, talk to us, and we'll try to explain it as best we can. There are other products we have access to as well. So ensembles, for example, I know we didn't go through that on these slides here, but we do have our own in-house ensemble products that we can offer. And again, that can demonstrate quite well to clients, because you've got your spaghetti. If it's all very nice and tightly packed together, you've got good confidence. If it spreads all over the place, making a terrible mess, that the confidence is going to be significantly lower. And again, describing it to clients like that as well can be quite helpful too.
Yeah, I guess just to add as well, it's all about when you're explaining to someone the risk or your confidence in something is to sort of simplify it and not go into too much technical detail, but just to make sure that you're kind of picking out the key points. What's the risk of this? How likely is something? And just to make it as easy to understand as possible for them, and not like a whole load of information to sort of confuse them, really.
Lovely. And time for one more final questions. We're 3 o'clock now. We've got a couple that have come through. How much verification can you do with your range of forecasts?
Sorry.
Yeah. So long as the forecast, so long as there's some observations either from our vessel or from a reliable external source, yes, we can. We can do. We can provide verification. It's as simple as that. So long as we've got data available at that particular site, which is, I'm sure anyone with a meteorological background will be aware of. Some places there's observations everywhere. Other places there's nothing at all. So it depends on the circumstance, basically.
Yeah, with the Fugro vessels, all the Fugro vessels have they all have wind data. A lot of them have wave data as well, and currents and things. So any forecasting that we can do for the Fugro fleet, we have kind of access to that, and we can see where they were, and so we can always go back and look at the data compared with the forecast, which is really useful. Especially if there's been like quite a tricky weather situation going on. You can think, right, let's have a look at all the different vessels and see what exactly was happening.
Lovely, and I'll squeeze one more in if no, they're still coming in, the questions. Yeah, are you embracing AI in your forecasts? It is a topic everyone is getting asked, and is sort of up there at the moment. Is that something that sort of you're playing more and more into?
It is, it is starting to sort of, we are aware of it, and we are doing over the next few weeks. Although Fred, I'm trying to think of the exact detail here, but we've got some work over the next coming up over the next few years where we are going to start looking into how AI models compare to NWP models, and whether they'll be of any use, or how useful they are or not, or where that sort of thing. It is all relatively new though, so I think I don't think I can really go any further in that, to be honest.
Yeah. As someone who has never not yet used ChatGPT, I'm still yet to see the benefits. I think it is interesting to see the verification of the different models, for sure.
We've still got some more questions coming in, so I hope we don't mind going over. What sort of operations have you got in the Aegean Sea?
So we haven't. So at the moment, we've not got anything up currently, but we have had some work from several clients over the years across the Aegean Sea, laying, I believe it was cables, if I remember rightly, to do with the Greek. I don't know if it was the telecommunications or electrical connection between all the different islands over the past few years. So we've been working on that, but we're not doing anything there currently. But yeah, it is one of the more, it's definitely one of the more challenging areas to forecast for, because of course you've got how the winds are interacting with the islands, how the waves are interacting with the islands. You can also get some pretty, when it's not just the Artesian winds blowing in that part of the world, you can get medicanes across parts of the Mediterranean as well. There's all sorts of things to consider for that part of the world sometimes. But that's sort of an overview. We work with lots of different contractors, both private and within Fugro. They're always moving all over the place. So sometimes we'll have a lot of work in one area, and then it'll get a bit quieter, and then it'll all come back again. And in the North Sea, for example, of course, when the weather is better towards the summer months, it tends to get busier there then, and then it quietens down over the winter when the weather deteriorates.
Yeah, and some projects only need forecasting for a few days to get something critical done. Other stuff might go on for a month or two, so it depends. Depends what they're doing, really. So
lovely, thank you. Final question: do you offer internships for sort of current MSc students, or sort of people who are interested in joining in the future?
I'm not sure actually on that.
We can offer work experience, and that can be just over a couple of days or a couple of weeks from time to time. I'm not going to go into too much detail because that's more to do with my manager and our human resources department than us. But yes, we can. Feel free to get into contact with us. I think is the best advice I can give. Yeah. And if there is anything about, we will get back to you.
Yeah, we can. Whereas we haven't actually got a contact thing, but we can, if it's something that anyone's interested in, I'm sure we can get in touch. Like I say, I don't know what the situation, how likely that is, but it's if you're interested, you can get in touch.
Right, brilliant. Well, thank you very much, both. That was really good insight. So thank you for your time, and thank you everyone for joining.
Thank you, everybody.
Thanks for having us. Thank you for listening.